added on 3 lessons to the Math 135 telecourse, and these I've called addenda because they're not in the current curriculum of the 135 course, and it's really pretty much assumed that you're going to be comfortable with this information. So the first one that we're going to look at here today is systems of equations, and I nicknamed it 2 by 2 if you've seen the Broadway show by that name. What we're going to do is work with solving systems of 2 equations and 2 unknowns. Now you did this in Algebra 1 and probably in Algebra 2 if you had those courses in high school, and that's one of the reasons we don't do it in the college algebra course. But I thought some of you might benefit from having kind of a refresher on how to work with systems of equations. Now to start out with, I always like to have you have an understanding of why do I care about this? And so I came up with what I deemed a reasonable problem that I might want to know the answer. So we've got someone working in the box office, and she was very reliable, did everything right, no problems making change, no problems with how much to charge, but she overlooked the fact that there were 2 different colored tickets, and she only sold 1 colored ticket. Now she did sell it at different prices depending on whether this person was a student, in which case they paid $3.50, or an adult at $6 a piece. So now you want to know, well, how many adults and how many student tickets did we sell? And here's the only information that you have. You know that you've brought in a total of $2,137 from the ticket sales, and you sold 402 tickets. So with that information then, I want to know how many of each type of ticket did you sell, or did Jelana sell? All right, well, to start out with, do you realize that there's technically 2 things here that I do not know? So I'm going to say let X equal the number of student tickets sold. And Y is going to be the number of adult tickets sold. Okay. Pardon the penmanship, but I do think it's really important that you clearly identify what your variables are, and it's even more important when you have more than one variable in the problem. Now, it is fine for us to work with 2 variables as long as we are able to write 2 equations. In fact, I think it's our very famous Mr. Gauss that proved you essentially have to have as many equations as you have variables. So what I want to do is see if I can find out 2 pieces of information that would allow me to write some type of an equation here. So one piece of information that I have is that there were 402 tickets sold. Well, if X is the number of student and Y is the number of adult tickets, how does that relate to the 402? Yeah. Do X plus Y, and you know the total number of tickets sold has to be 402. Okay. Now you know that equation by itself is not enough information for me to know how many of each, because it could be that you sold 400 of one and 2 of the other. Or it could be that you sold 200 and 202 of the other. I don't know. There's too many possibilities. So we need some other information. And the only other piece of information that I have is the total amount of money I brought in. Now this one's not quite as simple, so what I might want to do is give what I call a skeleton equation. Since I know that 2137 is the total amount brought in, I could say the money in student tickets plus the money in adult tickets. That has to total up to the 2137. And you see, the reason I call that a skeleton equation is that I kind of have the bare bones there. I don't yet have everything worked out, but I'm on my way. So now I have to stop and think, well, how much money would we have brought in student tickets? We know sometimes that's not always real easy to see. So I have suggested in the past that you consider working with some numbers. What if you sold 100 student tickets? How would you figure out how much money was brought in from those 100 tickets? Well, every single one of them is going for $3.50 a piece, so it would be 3.50 times 100, right? It'd be $350. Well, what if you sold 200 student tickets? Well, it's $3.50 a piece, so it'd be $3.50 times 200. Well, how many student tickets did we sell? X. Oh, so this is going to be $3.50 times X. And that makes sense. $3.50 times the number of tickets that I sell at that cost, that'll be the total amount of money I bring in student tickets. Now, with that in mind, you might pretty quickly see, oh, well, then the adults is going to be $6 times the number of adult tickets I sell. Why? Okay. So now I have a second piece of information, and I have what's called a system of equations. Now I'm going to rewrite that just a little bit. So I have x plus y is equal to 402. And I have 3.5x plus 6y is equal to 2137. All I did was take away the since, so to speak. And now this is a system because I have two equations, two unknowns. Do you remember how you've solved that in the past? Well, one very good way is to use what's called substitution. What I can do is I would go to this equation because he's my easier equation, and I might say, well, you know, I can see that y will equal 402 minus x. Let me make that look a little bit better. Then what I can do is, since this is the very same y as what is in my second equation, I can substitute in right here. So I can say 3.5x plus 6 times 402 minus x is equal to 2137. Now, do you see what happened there? Is this substitution came right down there in place of that y. And you say, but why do you do that? Because look at what I have now. I have an equation, a single equation, with only x in it. Well, then that means it's going to be solvable. It's a first degree. So let's clean it up. 3.5x plus, I think that's 2412 minus 6x is equal to 2137. And now you look at that and say, yeah, that's definitely a doable equation. So we have 2412 minus, what, 2.5 when we combine our like terms here. 2.5x is equal to 2137. So I would subtract the 2137 across and add the 2.5 across. Let's see here if I can subtract properly. 12 minus 7 is 572. I think it's 275. Okay, which means then that if I divide by the 2.5, and I believe that's going to be 110. So what did I just find out? Well, you know, it's so easy to get lost in the problem. That's one of the reasons why you write stuff down. I found that x is 110, so we sold 110 student tickets. Okay. But you know, I wanted to know how many of each type, so we have 110 student, and how would I find out how many adult tickets? Well, you know, I've got a couple of options, but right here is the very easiest. I know that there were a total of 402 sold, so that leaves, what, 292, I think, if I subtracted correctly, adult tickets sold. And you know, if you want to double check yourself, all you need to do is check to see if I sold 110 student and 292 adult tickets, will that be a total of $2,137? I think it will be. Okay? So I hope you see that there's a reasonable purpose in trying to work with systems. And now what I'd like to do is just focus on the basic algebra of what's going on here. And for the first few, I said I'd like to graph it and to solve it algebraically. There's a big advantage to that because I think it helps you to see what's happening. Now here's what I mean by graphing it. You first take one of your equations and just focus on that one equation. If I graph this, what's it going to look like? Well, that's a linear equation, and he's even in slope-intercept form for me. So I go to -5, and then I have a slope of 3. Well, that's 3 over 1, so up 3 over 1. Now I'm going to write several of them so that I can try to get a semi-straight line here. We only missed one, but hopefully we'll be okay here. You see, if you're working with a system, I don't strongly urge you to only use graphing as your means, but sometimes it can really help you get a sense of what your answers should be. All right, with my second equation, well look, he's already in slope-intercept form as well, isn't he? So I go to a +6. I have a slope of 4/5, so I go 1, 2, 3, 4. Oh, looky there. I hit that point exactly. Now, what does that mean? What does that graph tell me? The graph tells me that right here at the point of intersection, which happens to be 5, 10, 5, 10 should be a solution of this equation. It should also be a solution of this equation. It takes you just a moment to verify that, and then you realize, well, yes, that is the solution, 5, 10. X is 5, y is 10. Something else interesting, since these guys are both linear equations, there was only one answer. I found it, okay? Now, that's working it graphically. And when you work it graphically, you have to be very careful, and you have to hope that it falls on a grid point that you can find easily. So you also want to be able to solve this algebraically. Now, you look at your two equations, and you notice that they're both solved for y. So it's actually very easy for me to do the same thing that I did here. I can do a substitution. Because you see, with one equation and two variables, I can't solve it. All right, there's many, many solutions. Remember, in an early lesson, we talked about how that graph is actually showing you every solution to that equation. And so, since this graph is every solution of this equation, and this line is every solution of this equation, this is the only ordered pair that solves both. Okay, but back to solving it. Let's take what we know y equals from one of the equations and substitute it into the other equation. Okay? You know, just suddenly made me chuckle. I'm a big fan of John Madden. I hate it that he's retired from announcing in football because I love John Madden. And sometimes I always feel like John Madden when I'm circling and arrowing and all that. Substitution is a lot like in a football team. You know, let me digress for a moment. I apologize. And I don't know a whole lot about football, although I love it. But you know, if you've got an offensive line going on here, and I'm going to put 5 guys across the front. I apologize if that's wrong. But I know we've got the center here, and we put the quarterback behind him. Okay, we got wide receiver out here, and we've got tailbacks and so forth going on here. So anyhow, let's say that one of these, I think it's the guard that's right next there. Okay, anyhow, one of my offensive line guys. Now think about an NFL offensive lineman. Right? Okay. Well, let's say he gets nailed really hard and he gets taken out of the game for a rest. He'll be back. Now, are you going to ask this little wide receiver to come in here? No. Okay. Well, are you going to tell everybody, just slide down the line and we'll bring in a new wide receiver? No. What are you going to do? You're going to pull out that guard and you're going to put in his place, hopefully, a guard that is just as good as he was. So essentially what you're doing is you're substituting equals for equals. That's the idea of the substitution principle. And one of the reasons why I love the football, I know I don't have them all up here, is that everybody else stays put. The only thing that happens is that this one guy comes out of the game and somebody goes in his place, everybody else stays just where they were. That's the idea of substitution in mathematics as well. Okay? So in this particular case, everybody stays put, but this y is coming out of the game and the 3x minus 5 is going in his place. Okay? Now the nice thing is all you have to do is solve this equation. Yay! Bad news, fraction. Get rid of it. Since most of us don't like fractions, let's go ahead and get rid of it. And that would be by multiplying everything in this equation times 5. Why 5? That'll clear that denominator. So multiplying a 5 all the way through on both sides, I get 15x minus 25 is equal to 4x plus 30. And yay, all the fractions are gone. So I get 11x is equal to, add over, 55. X is 5. Now I know you say, well, I already knew x was 5. That's okay, this is verification. And you don't want to draw a graph every time you have to solve a system. Okay, for example, working this guy with a graph, oh, not nice. Look at that 2137. Yeah, you don't want to deal with that. Now, how am I going to find out the y coordinate? Well, it's actually another substitution idea. So think of John Madden again. We're going to take this 5 and we're going to put him in place of the x. Now, I can put it into either equation. You pick which one you like. Well, on your paper, I get to pick what I like, and I like the top guy. So then I have y equals 3 times the 5 minus 5. Now notice, like my football story, everything stays put. The y, the equals, the 3, the minus, and the 5. The only thing that happened is that that 5 went right in place there. And if you do that arithmetic, you get y is 10. And when you've found both of those variables, you have solved the system. Okay? All right. Well, let's go on to a second one, and we want to graph this guy as well as solving him. Let's just try to solve him first, okay? And you always want to kind of assess the situation. Sometimes students overlook that and they think that they should just dive in. No, you really want to stop and ponder for just a moment. And you look at that equation and then you look at this one and you say, oh, wow, he is solved for y. So I have two equations, two different variables. I'm going to take this negative 2x plus 1, and I'm going to put him right in place of the y. So I yank the y out, okay, and I have 2x plus, the y is gone, in his place goes negative 2x plus 1, and an equals 5. Everything else stayed put, y went out, negative 2x plus 1 went in his place. Now, my parentheses in this case are really totally extraneous. I put those in a lot of times just to clarify there's y. But they're preceded by a plus sign, so it's not needed. So essentially, I have 2x minus 2x, that's 0, and I get 1 equals 5. And you say something is definitely wrong. Something is definitely wrong because 1 doesn't equal 5. Okay, well, let's go and look at the visual picture of what should be happening here. So let me first, well, I'll graph this second equation first because he's already in slope-intercept form. I see that I have a y-intercept of 1, so I go to 1, and I have a slope of negative 2. So I go down 2 and to the right 1, down, whoops, from there, down 2 and to the right 1. Okay. There we go. Now for my second equation, oh, actually, he's real easy. If you have already watched some of the early lessons, I said when he's in this standard form, I like to find the intercepts, because if I let y be 0, you can see 2x equals 5 or x equals 2.5. Okay? And if I let x be 0, wipes that part out, and I get a y-intercept of 5. Now ponder that picture a moment. Remember what I'm supposed to be finding on the graph? This is all the values, all the pairs of x and y that make this equation true. And this red line is all the ordered pairs that make this guy true. And I'm looking for what makes both of them true. You know what it looks like? There is none. Well, let's take just a second here. On this first equation, 2x plus y equals 5, let's solve him for y. And we get y equals negative 2x plus 5. And then I want you to notice something. We've got a slope of negative 2. We have a slope of negative 2. What does that tell you? If we have equal slopes, parallel lines. As long as those intercepts are different, which they are, I have two parallel lines. So what will make both of these true? Nothing. And you know, here's what's interesting, is when you look at your result, you get 1 equals 5. You ask yourself, when does 1 equal 5? Never. No solution. Okay? Now, by the way, whenever that happens, I tend to think, oh, that's a little strange. I know it can happen, and I'll double check my work, try to make sure that I haven't made some silly arithmetic error. And if it's really important, I might graph it or verify from the slopes that I've got the parallel lines. Okay? But it is possible that you get a system of equations in which those two linear equations happen to be lines that are parallel to each other, and you have no solution. Okay. Well, this is our last guy to graph and to solve algebraically. And let's see here. if I thought you might like seeing this particular arrangement on my first equation. This is called the intercept form of a linear equation. Perhaps you've heard that before, but my guess is you probably haven't. It's usually skipped along the way. We have slope-intercept, we have point-slope. Here's another form, and it's kind of cool because remember how I have a tendency to find my intercepts? Like I cover this up because I'm going to put a 0 in for x, and I get y has to be 5. So it crosses the y-axis at 5. Then I put a 0 in for y and cover that all up. X has to be 4. By the way, do you see why that's called intercept form? Because it's really pretty sweet. Right underneath the x is your x-intercept. Right underneath the y is your y-intercept. Okay, so here's my line. Boom. Now let's graph this second guy. He's in slope-intercept, so I'm ready to go. And he also has a y-intercept of 5, doesn't he? And he has a slope of -5/4, so I go down 5 and to the right 4, and we end up, very strangely, with the very same line. What? Well, by the way, let's ponder that for a moment. If that's the case, then what ordered pairs make my system true? Because I'm looking for ordered pairs that make both equations true. Well, do you realize anything on the line makes them both true? Well, let's look at what happens to this guy algebraically. Okay? If I have x over 4 plus y over 5 is equal to 1, and I have y equals -5/4 x plus 5. Okay. Well, I'm going to do a substitution, and it might look scary to you, but I think we'll be fine. I'm going to take what y equals. I know what y equals. And then I'm going to substitute it for y into the other equation. So then I end up with x over 4 plus -5/4 x plus 5 divided by 5 is equal to 1. Now, do you realize that I can actually separate out that fraction? Now, the reason I can do that is that the way we add fractions is that if I have a common denominator, let's say I have 2/7 plus 3/7, how do I add that? Well, that becomes 2 plus 3 over 7. So I can go the other direction as well. I can split up that fraction. And I get x over 4 plus -5/4 x over 5 plus 5 over 5 is equal to 1. Then if we simplify, we get x over 4 minus x over 4 plus 1 equals 1. And another strange thing happens. We get 1 equals 1. And you say, when does 1 equal 1? Well, like all the time. Now, we do have to be just a little bit careful here. You don't want to say just anything will work. Because, again, our graph is very instructive to us. If I would pick the origin, 0, 0, you see that is not on either of those lines. So 0, 0 is not a solution to this system. Yes, I have infinitely many solutions, but all of those solutions lie upon that line. So what we usually do in this case is you can say my solution set, if you like, and it's always scary when we get into this fancy notation, but it's the set of all ordered pairs such that, that vertical line we read as such that, and take either of your equations. Y equals -5/4 x plus 5. Now, what that fancy notation is saying is my solution is every ordered pair that's on the line. I got lots of answers. Okay. Now, I did show you in this particular little segment one where we had one unique solution. Our lines intersected at that point. That's what we have happening most times in our systems. But then I also showed you the two oddities, that sometimes we get no solution and sometimes we get infinitely many solutions. Okay? Now, what I'd like to do is just go ahead and work some more of these algebraically. Now, we have been working algebraically, and we've been using what process? The John Madden process. I hope he doesn't mind me using his name. Or the substitution method, okay? But there is also a second way to solve your systems. And as I look at this particular system of equations, I see that it's not ready to do substitution. I don't have one of these equations saying x equals or y equals. Now, it wouldn't be real hard. I could solve this guy for x without too much grief and substitute in. But there's an easier way. And I gave you a picture of a balance here. Perfect scale balance. You realize that an equation is essentially a balance. Right now, we've got 3x minus 2y balancing 6. Now, I also have x plus 2y balancing 10. So do you realize that if I add the x plus 2y over on this, on the left side, and I add the 10 on the right side, won't that stay in perfect balance? If you understand the concept of equations, you'll realize, well, yeah, if I'm adding two equations together, it makes total sense that it's still going to be in perfect balance. I still have a valid equation. Now, by the way, when we add equations, we always line up the equal sign. You know, it's kind of like when you learn to add decimals, you'll learn to line up the decimal point. We line up the equals. And you want to add left sides together, right sides together. Okay? Now, when I add over here, you'll notice that the 3x plus x gives me the 4x. And negative 2y plus 2y, they're gone. By the way, that's why this was a good option. Because then when I add over here, I get 16. And now I have this lovely, small, easy equation, and I know x is 4. Okay? Now, have I solved my system? Not yet. I know half of my solution. I need to find the y coordinate now as well. So I can choose either equation. You pick which one you like. I'm going to use the second one. X plus 2y is equal to 10. And I'm going to put this 4 in place of the x. I'm still doing substitution, huh? And I get 4 plus 2y is equal to 10. 2y is 6. Y is 3. So my solution is 4, 3. Hey, if you're solving a system, it is a good idea to write it as an ordered pair, or if you have 3 unknowns, ordered triple. And if you have letters, well, even with the x and y, whenever you have your variables, you put them in alphabetical order. So if you have A and B, put it in A, comma, B order. Okay? And if I want to double check myself, I can put 4, 3 back into that original equation. Hopefully I get 6. Put 4, 3 into the second equation. Hopefully I get 10. And then I know I have the correct answer. Yeah? So this is called, by the way, the elimination method. Do you know why it'd be called elimination? Because what I did is, through addition of the equations, I was able to eliminate the y's out of the equation and get one equation with one unknown, which is my goal. All right? So you have two ways to solve these. Well, technically you have three if you count graphing, but I do not really consider that a reliable way to generally solve my systems. I love it as a support system for me, but I don't generally like graphing as my main solution, my main algebraic solution. Okay, well now we get 3x plus 8y is negative 5, 2x, ugh. And when you see the directions solve, you've got an x and a y. It means find out what each of them is. Thankfully, I have two equations since I have two unknowns. By the way, that's that whole 2 by 2 at the very beginning. If I could sing and dance, I'd sing that for you, but I won't. And then you ponder, because that's just not a pretty sight. I look at that and I say, you know, he's not ready to substitute because I don't know what x is or what y is. And when you ponder your options, like, should I solve this equation for x? Ew. If you think about the options, they're not good. Okay, so then you think, well, maybe I should use elimination. Well, for right now, I add those equations up. Do I drop out my x's or drop out my y's? Oh, but there's something we can do. What we can do is we can multiply through these equations. And here's what has caught my eye. I've got this 2x and the 3x. What I'd like to do is multiply them both up to 6. Essentially what I'm doing is I'm looking for the least common multiple of these two numbers. Now if I wanted to eliminate the y's, I could multiply 8 and 5 up to 40. But I've decided this looks easier, smaller numbers. Now I would also like one of them to be negative, so that when I add, I have a negative 6 and a positive 6 and they drop. So here's what I'm going to do. I'm going to multiply this top equation by negative 2. Now that is totally legal. I am allowed to multiply all the way through an equation by anything I like except 0. So that would give me negative 6x minus 16y is equal to positive 10. Are you agreed with me? Multiplying through by the negative 2? Well, then I go to the second equation and I want to have a positive 6x, so I multiply through by a positive 3. And I get 6x plus 15y is equal to negative 10.5. Yeah? Now these are equivalent equations to the original two that I was given, and what works out really nice is that now I can add these two equations up. And in the process of adding, I've lined up my equals. Negative 6x plus 6x, the x's are eliminated. And I get negative 1y is equal to negative 0.5. So y is equal to 1/2, or 0.5, whichever way you like to look at that. Okay. Now you know I now have half of my answer. I have to go back and find the x. Now I can choose to put that 1/2 into the second equation or into the first equation. And if you're really good with arithmetic, you'll notice that the first guy will probably be easier for us. So I get 3x plus 8 times 1/2 is equal to negative 5. And I get 3x plus 4 equals -5. Subtract your 4, divide your 3, x will equal -3. So I have -3, 1/2. And notice that with that fraction, that one would have been a little bit more difficult for me to find the solution just by graphing. It would have been a very tedious situation to make sure I hit it there. Okay? Well, I decided to be a little bit tricky with you here. And we've got a nonlinear equation. Well, now if you've already gone through this course, you should recognize that top equation as a parabola. If you haven't yet gone through the course, well then be patient. I'm maybe being mean to you. But this top equation is not a straight line because of that exponent. He's a parabola, and he has a vertex sitting at 0, -4. And he's opening upward. Now I'm just making a really rough sketch there. Then this guy is a straight line. He's crossing the y-axis at 2, and he has a slope of 1. Now the reason I made that really quick sketch, I'm not getting my answers from the graph, but look at that. Remember, I'm looking for ordered pairs that make both equations true. And that means that I'm going to probably have 2 solutions. Unless I've done a horrible job of graphing, there are 2 solutions to this particular system. And that's kind of interesting to know as we work through. Now, as you look at this system, I see y equals and y equals, and I say, oh, I'm ready to play John Madden. Y is out. I can substitute in there. In this case, I wouldn't use elimination. Because I had equations solved for y, substitution was my path of least resistance. So I get x squared minus 4 is equal to x plus 2. Okay? Well, let's bring the x over, bring the 2 over, and we get x squared minus x minus 6 equals 0. Remember how we solved this? Factoring if possible. If not, use your quadratic formula, but it factors pretty easily. And then we use our zero product property. If these 2 quantities multiply to be 0, x minus 3 is 0, or x plus 2 is 0, and we get x is 3, or x is -2. -2, positive 3. Oh, you see, that's what I mean by letting the graph be support for your algebraic work. Now, I'm not done. I need to find the y-coordinate, and I can use either equation. This guy looks easier to me. So I would say y equals 3 plus 2, y equals 5. So I have one solution of 3, 5. Seems very reasonable. And here, if I put the -2 in, -2 plus 2, y is 0. -2, 0. I had 2 solutions, and there they are. That's kind of neat. Okay. Well, I decided to be tricky one more time. And this one, I think what we'll do is maybe just look at it graphically, and I'll just tell you a little bit. We're not asking you to do this generally in college algebra. I just thought it was a reasonable thing to consider. So let's look at the graph of what would go on there. That top equation, y equals 5 minus absolute value of x. If you've already gone through the lessons on transformations in this course, the graph of y equals absolute value of x is a V. sitting at the origin with its point at the origin. And this minus sign is going to flip him down, and the 5 is going to move him up 5. So 1, 2, 3, 4, 5. There's my absolute value graph. Rough sketch, that's all I'm doing right now. Well, let's see here. Y equals negative 2/3 x. I hope you realize that that's a linear equation. He goes through the origin, and he has a slope of negative 2/3. So, by the way, this is not going to be parallel. I didn't hit that very well, did I? You're going to have essentially two solutions because these guys will, if I had done a better job of graphing, it's probably more like this. Oh, yay, it's going to work. Let me fix my graph just a teensy bit. Y equals negative 2/3. It's going to be a little bit more slope than I had it. This guy has a slope of negative 1. And what I wanted to point out to you is that by being able to graph these equations and looking at my system in this way, I realized that I could take the equation of the line for this part of my absolute value. You can write that equation easily along with this equation and solve that system. I can do the same thing for this one. I know that we have got a y-intercept of 5. This one has a slope of negative 1, so it'd be negative x plus 5. This guy crosses at 5. He has a slope of positive 1. And so I thought that was kind of an interesting idea to split it into two systems because of the absolute value. Well, that was kind of taking you a little further than you needed to go, but I thought it was an interesting kind of addition. So just a quick recap for you when it comes to solving systems of two equations and two unknowns. You might need to solve one of them first for one of your variables, but then you can substitute back in. And actually, if you have systems that are not linear, where both equations are not straight lines, you're really better off using substitution most times. Now, if both of your equations are linear and they just lend themselves more to elimination, that can be a very quick way to solve that system of equations. Well, go back and practice with your substitution, your John Madden kind, and practice with elimination, okay? And get proficient with solving systems. Bye.